Hi everyone, I am Shamali, Assistant Professor at SPC. Today we are stepping into the fascinating world of computer vision, a field that teaches computers to see and understand the world just like we do. So, from unlocking your phone with a face recognition to self driving cars that detect obstacles, computer vision is everywhere around us. In this session, we will explore its core concept, real life applications, and how it shapes the future of technology. Let's begin the journey of teaching machines to see and think visually. In this unit, we will be learning how computers can move beyond flat 2D pictures and actually understand the world in 3D, just like our eyes do. The process is called 3D reconstruction and depth estimation. Depth estimation is about finding out how far objects are from the camera. And once we know that, we can build a full 3D model of the scenes. So you're already seeing this in actions from AR filters that fit perfectly on your face to 3D scan in healthcare and even self-driving cars that detect distances. We will explore two main approaches. First one is about the passive method, which relies on the regular images and lightning, and active method that use special sensors like laser or depth cameras. By the end of this unit, you will see how machines turn ordinary photos into a 3D world. So let's go with the topic on, like, have you ever wondered how your phone creates a 3D face scan, or how self-driving cars know exactly how far another car is or away the car is? So this is the magic of depth estimation and 3D reconstruction, turning the flat images into a 3D understanding of the world. So, some of the real time examples we can say, like when you use your Google Maps 3D view, or when doctors scanned bones in 3D. So, these like x rays, or even when Snapchat add filters that stick to your face perfectly, or all of this powered by 3D construction and depth estimation in computer visions. Or some of the examples like human analogy, like think about how your eyes works. Each eye sees a world slightly differently, and your brain combines those views to estimate the depth. Computer vision does something very similar, using images or sensors to find out or figure out what is near, what is far, and then building a 3D model. Or the futuristic vision, like imagine a world where a robot can move safely around us, where virtual reality feels completely real, and where AI can scan and rebuild the entire cities in 3D. That's where 3D reconstruction and depth estimations are taking us. Or some of the archaeological find of finding the previous kings' faces or any pyramid models over there. Pictures don't fly in over disaster site, or it does not just see flat photos. It creates a 3D map of the area, helping like rescuers finding people trapped around under a rubble. That's the real power of depth estimation and 3D constructions. So these are some of the examples I can say to understand the basic idea about this 3D reconstruction and depth estimations. So let's go into the real-time examples. The first one is autonomous vehicles or a self-driving car. Many things that are coming into picture in the futuristic. So think about a self-driving car. It can not rely only on flat images like 2D from a camera, right? So it needs to know how far everything is. So that's where the depth estimation comes into the picture. So the cars use a LiDAR or the LiDAR sensors like laser and scanners to sweep the environment and create a 3D point cloud, which is basically a map made of millions of tiny dots. This data is then combined with the camera images that estimate the depth. So the car can see the pedestrians or the road markings and the other vehicles all in a 3D view. Without this, the car have no idea when to stop or turn safely. Second one we can say about the robotics. So in factories, the robots need depth perception. Imagine a robotic arm on an assembly line, fine. So each part might not be in an exact same spot every time. So the robot uses sensors like structured light, projecting the pattern onto the objects and measuring how they bend. So to figure out the exact shape and position with this 3D information, the robot can grab the object with a perfect accuracy as well as to continue its task. So like assembling a phone or a packaging goods, right? So these are the two examples. We have more examples. We go for that. Next one is augmented reality. We call AR, VR or AR. So ever place a virtual chair in your living room using an AR app? That's depth estimation at work. The AR systems calculate the depth to ensure that the chair sits on the floor and can even be hidden behind a real table. So this realisms, right? So known as occultation, makes AR more conveniencing or convincing the blending virtual object seamlessly in the real world. Next, we can talk about the gaming and environment. Everything we are seeing is all about the games and more on entertainment way or the video games. So in the video games and movies, like creators using the photogrammetry, it's a technology used in this field to make them more entertaining way. So taking hundreds of photos of real objects or scenes from a different angles to reconstruct the detailed 3D models we use in on. So these lifelike models are then used in a game engines or special effects, giving us a realistic environments and characters. Some of the examples for the last I can say is medical imaging and surgery. So surgeons often need more than a flat 2D images, right? So with a stereoscopic cameras or two cameras working like a human eye, doctors get a real-time 3D views inside the body during like minimally invasions surgeries or this passive depth estimations improve the precision, maybe used in laparoscopic or many other technical harm. So hand-eye coordinates and the patient safety. So these are some of the example I can say it is work in a real world today. So, in computer vision, one of the most important goal is to understand the three-dimensional shape of an object, right? From a flat that I call as a two-dimensional images. So, as a human, our brain it does it effortlessly when we look a photo, we can tell that something is round or bumpy or slanted, right? But for a computer, this is not so straightforward or not a very easy way to detect it. To solve these challenges, researchers developed a family of techniques known as a shape from X. So the shape from X here, X represent the type of the visual cue being used. So it could be shading or any texture or the motion or any other features in an images. So each cube provides the different information that helps estimate the shape of an object. So one of the classic method is shape from shading. We call that as a SFS, shape from shading. So this technique works by studying how lights fall on a surface. So for instance, imagine a smooth white ball lit by a lamp. The side facing the light appears bright while the side in shadow appears darker. So, by analyzing these gradual changes in brightness, a computer can figure out that the object is round and flat or not flat. So this methods relies on like the knowing the directions of the light source and how the surface reflect the light. Basically the play on the light and how the directions over that. So another approach in SFS or S come to SFT, the shape from a texture. Last we have seen about the shading, shape from the shading. Now we are going to see about the shape from texture. So here the idea is that texture changes appearance, right? Depending on their orientation, the space, or for example, think of a tile floor in a photograph. The tiles closer to you look larger when compared to the shorter way, right? And evenly shaped, right? But as a floor stretches away from the camera view, the tiles appear smaller and squished. So, by measuring this distortions in a pattern, a computers can estimate the depth and the orientation of the surface. So, together, these techniques, the SFS as well as STF or SFT, these techniques and many other under the shapes from X umbrella, right? So allow computers to reconstruct these shapes from the ordinary images. They bridge the gap between the flat pictures and the real world geometry, making applications like robotics or any augmented reality and the medical imaging as possible. So these are some of the intro about the shape from X. So let's see another powerful method under shape from X. It's already seen about the shape from texture. These techniques relies on how patterns look differently depending on the distance and orientations. This and all we have seen already. So this is about the shape from focus or defocus. So which makes use of a blurring image. We have all seen portrait photos when the person's face is crystal clear, right? So, but the background is beautifully blurred. The popular bokeh effect or this blur is not just for aesthetic. It actually carries useful depth information. A shape from focus algorithms analyze how sharp or blunt the different parts of the image are to estimate how far each region is from the camera. So the sharper the object, the closer it is to the focal plane, or the blurred it is, or the farther away. So finally, we have the SFM, that is the shape from motion, which extracts the 3D construction from the movement. Or if we capture a sequence of images as either the cameras or the object moves, we can track how features shift across frames. For example, in this video of the person's walk-in maybe is given, we could track a single point like the tips of their nose by following its path across the consecutive frames. The computers can triangulate its position in a 3D space specifically. So repeating this process for many points allows the full 3D shapes of the people to be reconstructed. Together, these examples show how even subtle cues or the texture changes, the blur or the motion, can give a flat image the missing dimension of the depth, allowing the computer to see the world more like we do. So next we can see about the active range finding. So let me give an intro about this. So when a computers need to estimate the depth, they don't always rely on the existing light or the multiple images. Instead, they can actively send out their own signals like laser, light, or even sound, etc., and measure how these signals bounce back, right? The reflections of what we have done as an action. So this approach is called as an active range finding. So by projecting something into the environment and carefully studying its reflection, computers can measure distance with high accuracy. So this is especially useful in a dark or textureless or any underwater environment we are using today where passive method fails. So we are going for this active range finding methods. There are many more real-time example we can see on that. First, I will start with the structured light. So this methods projects a known pattern basically, such as stripes or the grids on the into an object. So a camera observe how the pattern bends or distorts on the surface. The and form this deformation. So the 3D shapes can be reconstructed, right? Examples I can say like Microsoft Kinect V1 projected an invisible infrared dot pattern. A camera captured how the dots were distorted on an object, projecting a depth map that allows the games to track body movements. So this is one of the real-time examples, or I can talk about the TOF, the time of flight. In this method, the systems emits a short pulse of light, or I can say as a laser, and measure how long it takes to bounce back from an object. Since the speed of light is constant, the round trip times gives the distance. For example, like modern smartphones with the LiDAR uses, I told discuss about before itself. Here uses a TOF sensors for AR app, scanning rooms or many things are there, or by object by sending laser pulse and measuring the return times basically generate fast as well as accurate 3D maps. This is one of the applications of the work on this. Next we have to talk about more examples. We'll see on to that. Next is laser triangulations. Here a laser line is projected onto a surface and a camera records its position. The angle of the reflected line changes depending upon how far the object is, which can be used to reconstruct in a 3D. I can say some of the example like 3D scanners in manufacturing uses the laser triangulations to scan the object for quality controls as if the laser lines moves across an object. The camera records the distortions and built a precise 3D models. So next I can say about the acoustic sensing. Instead of lighting or the light, this method uses sound waves. It sends out an ultrasonic or sonar pulse and measures the time taken for the echo to return. For example, the sonar systems on submarines emit a ping and listen to the returning echoes to calculate the distance and even map the underwater object or the seabed. So these are some of the examples I can say. To wrap up thing together, these techniques like structure light, or we have seen about the TOF, laser triangulations and acoustic sensing, and show how computers can actively exploring the surroundings rather than passively waiting for informations. So whether it is a gaming with the Kinect, the Microsoft, or the scanning objects in factories, or measuring rooms with the LiDAR in the smartphones, or detecting the obstacles in underwaters, active range findings gives machines a reliable way to build a 3D understanding of the world. Next, we can talk about the surface representations. So, when we talk about the representation in a 3D object in a computer visions and graphics, we need a way to describe these surfaces so that computers can store, manipulate, and render them. These are called surface representations basically. So each methods offer a different balance between accuracy, efficiency, and flexibility depending on whether the application is gaming, animation, CAD, or CAD, or scientific modeling, right? So there are many types of the surface representations. First, we can start with the polygon mesh. So this is a most widely used method where a 3D object is built from the connected polygons, that is usually in triangles or quadrilaterals. So a mesh is defined by vertices, edges, as well as surfaces. Example, I can say a character model in a video games, right? They will be constructing the characters using a polygon meshes only. So these meshes often consist of thousands of a tiny triangle that form the surface of the characters. Next, we can talk about the implicit surfaces. Instead of explicitly listing the verticals, and implicit surface is defined by a mathematical function. So the surface is a set of points where the functions equals to 0. So this method is memory efficient and create a grade for handling the smooth deformations or changes in the topology. For example, you can talk about the sphere can be represented by the equations like x square plus y square plus z square minus r square is equal to 0, the radius. So this compact form describes a sphere without needing to store thousands of verticals. Next, we can talk about the parametric surface. Here, the surface are described using the parameters. Commonly, we can say U and V, the map to point in 3D space. So this method is very flexible and often used in engineering and designs. For example, a parametric sphere can be expressed as x is equal to r sine or u and cos of v. So y can be represented as r sin or u sine v. So is it also r cos t u? So basically, these are things will be represent for x, y, and z. So this approach is widely used in CAD software for designing the precise curves and surfaces. We can next talk about the subdivision surfaces. So these methods begin with the coarse polygon mesh and repeatedly subdivides and smooth it to create a detailed. A smooth surface is combined the simplicity of polygon meshes with smoothness of parametric surfaces. Example, we can say in the animation tools like Blender or Maya, subdivision surfaces are used to create smooth organic shapes such as characters, like faces or the creatures are basically in the characters. So bodies starting from a basic low poly mesh. So these are some of the things we have seen. To wrap up things in short, polygon meshes gives us flexibility for games and graphics, or the implicit surface provides a compact mathematical descriptions. The parametric surfaces enable precise modeling for engineering, and the subdivision surfaces deliver smooth organic model for animation basically. So choosing the right representations depends upon whether the focus is speed or memory efficiency or the realism. Next, we will see about the point-based representations. So, while the meshes and surface rely on connected edges and faces, another way to represent a 3D object is through a point-based representation. Instead of describing the object with the continuous surfaces, the object is represented as a collection of discrete points in a 3D space. This approach is particularly common in real-world scanning technologies basically. So here like a LiDAR in smartphones or the depth cameras where the raw data is often captured as a millions of tiny sample points. There are many types of point-based representations. First, we'll start with a point cloud. Okay, so a point cloud is simply a large set of points in a 3D coordinates. For example, x, y, z. These are the 3D coordinates. These points don't carry explicit connections like edges or the faces, but together forms a shape of an object when viewed as a whole. So the point clouds are one of the most common raw output from the 3D scanning systems. For example, I can say, as usual, the LiDAR scanner of a room produces a dense cloud of millions of points. So here, each point corresponded to a spot in a room. So together creating a detailed 3D representations. So this is all about the point cloud. There is another thing called as a point sets. So the point sets are similar to a point cloud, but often come with an extra attributes. So these can be include like RGB or the surface normals, we can say, which tells the orientation of the surfaces basically. So, or even a radius that define the influence of each point in a space. So these makes the more powerful for analysis and rendering. Example, I can say a 3D scan of a statue might use a point set where each point carries or both the color value for surface detail and a normal vector indicating the surface directions at the locations. So this allows for more accurate rendering and reconstructions. To wrap up about the points, I can say point based representations are lightweight basically and directly tied to a real world 3D data captured. So the point clouds we have discussed before gives a raw spatial structure, while the point sets enrich these points with additional attributes for more detailed and usability. So they are essential in applications like autonomous vehicles or driving, so like LiDAR scans, or the 3D reconstructions like AR, VR, and any heritage preservations here. Another things we have to see is the point based surfaces. So here instead of just treating the point as a raw samples, the point are understood as lying on continuous surfaces. In this is a little more advanced. So by approximating the local geometry around each point, algorithms can reconstruct a smooth surface from the point data. So this makes point based surface very useful when visualizing or reconstructing the large scale 3D scans. So for example, I can say a rendering technique can take 3D scans of an archaeological site, just like a temple wall, for example, and use a point based surface to display it smoothly, basically. So, without needing to build a full polygon mesh. So that's how the point based surface works. A little more advanced than the before. Next, we can talk about the normal based point clouds. So, in these approaches, each point is enriched with a very normal vectors that we can say is a direction perpendicular to the surface at that point, basically. So that extra informations allow the system to better estimate the surface orientations, which is crucial for shading or rendering or any mesh generations. For this, maybe there is an examples for a structure like a light scanner not only capture the 3D locations of each point but also record it which directions the surface is facing and like that. So these makes the reconstructed 3D objects look more realistic when lightning and shadows are applied. So these is a little bit changes in when compared to the pure techniques. Next, we can talk about the volumetric representations. So far, we have looked at a surface-based or the point-based ways of representing a 3D objects. So, but there is another powerful approaches. It's called as a volumetric representations. So instead of just describing the outer surface of an object, volumetric methods describes entire volume of a space that the object occupies. So this makes them especially useful for applications where we need to model both the inside and outside of an object, like medical imaging or physics simulations or detailed 3D modelings. There are many types. Let's see one by one. The first one here is a voxel grid. Think of a voxel as a 3D version of a pixel. A voxel grid spaces is divided into a tiny cubes we call as a voxels, and each voxels stored a value that tells us whether it belongs to an object or not. Example, a CT scan of the human body stores data as a voxel grid. Each voxels represent a small cube of tissues basically. So when its value showing the tissue density, this is perfect for capturing the complex internal structures like bones or the blood vessels and the organs. So this is all about the voxels grid. The next one is a SDF, signed distance function. So as a SDF is a mathematical function that tells you how far a point in a space is from the object's surface. So if the point is inside an object, we consider as a negative value. If the point is in outside, we consider as a positive value. If the point is on the surface, we'll consider as a 0. So basically there is 3 consideration. One is negative value, positive value and 0. This representation is very flexible, smooth, making it useful for modeling or any rendering and physics. So example, in a 3D sculpture software, the SCFs allow artists to combine the shapes easily, like merging two clay balls or Boolean operations like union, subtractions, and intersection are straightforward when using STFs. They are also heavily used in collisions, reactions in games, and any realistic rendering techniques. Maybe for two-phase combined, what will be the result? There are many more techniques used for this. To wrap up the things, the volumetric representations go beyond just the surface and capture the full 3D space of an object. So the voxel grids are discrete and widely used in scanning and medical imaging, while SCFs provide a smooth mathematical representation ideal for modeling and simulations. So, together they form the backbone of many advanced applications in healthcare, like graphics, and robotics. There are also more technique like occupancy grid. An occupancy grid is a simplified voxel grid where each voxel stores just a binary value. Like one will be occupied basically. So there is an object here, that is what it is represent, or zeros will be represent as empty or free spaces. So this makes it lightweight and practical for real-time applications like robotics. A robot does not always need a fine surface detail. They just need to know where the obstacles ought to be avoided or the collisions. So, example, a robot, a vacuum cleaner. We can speak right now. So, basically, this robot vacuum cleaner built an occupancy grid for your living room. So, the walls or the furnitures and any obstacles are marked as 1, while the free space is marked at 0. So this allows the robots to safely plan its path. So this is how the robotic vacuum cleaner works using the occupancy grid. So next we can talk about the level sets. So the level sets takes the volumetric representations a step further by focusing on how surface changes over the time. A level set is usually based on the sign distance function we call as SDF, and represent the object surface as a set of points where the function is equal to 0. So the real power of level sets is tracking varying shapes. For examples, in a fluid stimulations, the shape of the droplet or the water changes constantly. Levels or sets are used to update the droplet surface as it moves or splits or merges. So, giving the smooth, realistic result in animations and scientific visualizations. So, these are things we have seen. So, to wrap up the things, the occupancy grid simplify the space into the binary, which is a free, basically binary, like occupied or free, zeros as well as ones, so making them ideal for real-time robotics as well as navigations. So the level sets are dynamic and powerful for modeling the shapes that changes over the time, like aging, like fluids or deformable objects. So together they show how volumetric methods can be adapted for very different needs, from a simple mapping to advanced simulations. Next, we will speak about the model based reconstructions. When reconstructing the 3D shapes from 2D data. Sometimes the information we get is incomplete or noisy. Instead of starting from scratch, a powerful approach is to use the model based reconstruction. So, here we begin with the predefined 3D models like a template and then deform or adapt or constrain it and to fit into observed data like images, videos, or point cloud. So, this makes the process more robust, especially for objects with the predictable face shapes like human face, hands, or organs. There are many types of model based reconstructions. First, we'll see about the template fitting. So here, a genetic or the generic 3D models like template is deformed to match the observed object. This is especially useful when object belongs to a well-known category. Examples in a smartphone, face recognition be used like a generic 3D face model is adjusted in a real time aligned with the user unique facial geometry. Statistical shape models. Now imagine you are a doctor trying to analyze the shapes of a patient's art from a medical scan. Okay, so no two hearts look exactly the same. Some are wider, some are narrow. So how do we handle that? That's where the statistical shape models come into the picture. Instead of just one clay sculpture, think of the whole library of art sculptures. Collected through the thousands of patients, you look for the common patterns like the average heart size, or you also learn how heart vary, like bigger chamber, smaller chamber, etc. So these are the variations you can see among the hearts. So, when a new patients come in, you don't start from the scratch. You say, this heart look 80% like this average one. Or but stretched is like slightly here and bend there. Only the similarities you can notice on. So it will be better for the differentiated. That is a powerful but because it lets us deal with the natural variations in the real world. One famous example is the active shape models, which has been used to automatically segment the verticals in the art scans. Next, you can see with the deformable models. Deformable models, like think of them as an elastic band or a rubber sheet. They have this ability to bend and stretch, but they also resist bending too much, right? So here is a classic the snake model. The picture dropping a rubber band near the outline of an object in a photo. So slowly the band begins at the base to stick to the edges like a snake slithering under its the boundaries. So this is super useful in the medical imaging. For instance, when you are trying to find the exact boundary of a tumor, this nice part it is like they don't just fly off in a random directions. They balance between the flexible enough to fit the data and rigid enough to stay realistic. So this is all about that. Next one we are going to see about the prior based reconstruction. Finally, let's talk about this prior. Basically, the common sense baked into the model. Like, let's say you take a single photo of me sitting in a chair. My arm is hidden behind the chair, right? So, according to the perception. So, how could a computer guess what my arms look like if it cannot see? This is impossible if you rely only on raw pixels. But if the system has a prior knowledges, like it knows humans' arms usually attach here, bend this way, and have this length, maybe the prior knowledge of that. It can fill in the missing pieces. Like this is a critical in applications like reconstructing full 3D bodies from an image, or even the generative avatars in a virtual reality. I can say some of the example like pyramid 3D model reconstructions, or the recent trends in a Gemini AI, like the retro looks that we recreating using the pictures we have been uploaded to that. Without the prior, the system would just leave the gaps or make wide guesses. So with the prior, it builds something realistic and consistent. So we can just wrap up on this. So to recap, the model-based reconstructions is all about the starting with the knowledge instead of starting from the scratch, basically. So with the template fitting, we mold generic shapes to fit. With the statistical shape models, we have learned from lots of examples. With deformable models, we let shapes flex and stretch to fit. So with the priors, we use a common sense to guess the hidden pattern or the parts. The beauty of this approach is it saves times, reduces ambiguity, and often gives more realistic results. Now think about this, like what if we combine this image, imagine using statistical model of a human face plus prior about the expressions plus the deformable properties. That's exactly what powerful powers, like some of the most advanced we can say as AR filters or VR avatars and medical imaging systems today. So the next time your phone unlocks by scanning your face, remember it's not just a camera taking a picture. It's like a sculptor blending a 3D model to match you in a real time. So that's how the magic works in the technologies. Next, we can talk about the recurrent texture maps and albedos. I'll start with an interaction here. Okay, so far we have talked how about to get a shape of the object in a 3D. But if you're ever sensor or seen a plain 3D model, just gray polygons, or it does not look very convincing, right? So what makes it realistic is the visual details, the color, the pattern, or the way the surfaces reflected the light. So that's where the textures maps and albedos comes in. So these are the techniques to make the 3D reconstructions look real, not just the geometrical skeletons. As we discussed before, it's all about the Gemini, the recent trends. you can say it is more realistic. Even though it is a 3D model or the constructions of your face, when compared to the other trends or any Ghibli styles, whatever it is, this Gemini AI is more realistic other than like a geometrical skeletons. So today let's step into the step-by-step process of texture mapping and the albedo estimations, photometric stereo and multi-view the texture mappings. So we can see one by one. Let's start with the texture mapping. Imagine you have a cardboard box on its own, like it adjusts as a plain brown. But what if you print a photo of a built-in face and carefully wrap it around the box? Suddenly your cardboard box looks like a tiny building. That is a texture mapping. In a computer graphics and vision, we take a 2D images, a texture map, and wrap it around the surface of a 3D model. So, example for your understanding is that let's say we are reconstructing a 3D geometry of a building from a drone scan, from the drone view of that. So, to make it realistic, we project the actual photos of the building's windows, bricks, and even more doors like onto the 3D geometry. Now, instead of a lifeless model, we have something look like alive or realistic. So this is all about the texture mapping. The texture mapping is everywhere, like video games, movies, VR, virtual reality. Without it, everything would look like a plain gray clay. So that's not so appetizing to us. So when come to the albedo explanation, now let's get a little more deeper onto this. A photo is a mix of two things, right? One is the real color of the surface, that's what we call as the albedo, and the lighting conditions. Here is an example. You take a picture of a white wall under a yellow light. The photo looks like yellowish or the angle of that, but the wall's real colors is white actually. It's called as the albedo. The real color of the albedo is white. So how we do the separate the lighting from the surface true color? That's what albedo estimation does. Why is this useful? Imagine a medical imaging where lighting can distort the tissue's color, or the AR applications where your avatar shirts should not look neon green just because you are sitting under a green lamp. Estimation albedo helps us to find the object true color, right? So we have to differentiate it. That's where this albedo estimation come into the picture. Next, we can come over the photometric stereo. Here is a cool technique like photometric stereo. It's a very cool when compared to the others. The idea is very simple. You take multiple photos of the same object from the same camera position, but with lightings or the light shining from a different direction. Then you analyze how brightness changes to this for training the model. So this will be useful. So think of a coin. If I shine light from the left side is brighter and the right side is shadow comparatively. If I shine from the light from the right, the opposite will be happen. That is a vice versa pattern. By comparing these shading pattern, we can figure out the surface orientation at every point, like a surface normal, right? So, and here's a bonus. We can also estimate the albedo from this process because we are factoring out how much of the brightness is due to the light versus the actual color. Example, we can say a camera takes 3 pictures of coin with the lights at a different angles. From the shading, we recover the coin surface normals and know that the coin instinct color is metallic silver, right? This is how this albedo explanation is worked on. Next, we have to talk about the multi-view texture mapping. Here, so far, we have used one image at a time, or at least 3 images. But what if we have a whole collection of images? Say a dozen of photos of a statue from a different angle. Or the multi-view texture mapping combines information from all those photos. It stitches the best texture patches from each image onto the 3D models. This solves 2 problems. One is the occultation. We call it if one side of the statue was hidden in one photo, maybe another photo might show it. So it is easy for us to build on that. Next is the seams. Instead of one stretching texture, stitching multiple images gives higher resolution and fewer ugly seams. So this is how cultural heritage projects build stunning 3D digital replicas of statue and monuments, high detail, no gaps onto that. So this all is about worked on this. I just wrap up with thing like reflections, like so recovering a texture and albedos is all about making a 3D reconstructions look real, right? So the texture mapping wraps 2D images on a 3D shapes basically. So the albedo estimations finds the true color over that, like independent of lighting. The photometric stereo uses a shading to recover the surface normals and albedo as well as. So the multi-view texture mapping blends multiple images to create seamless texture. So if a geometry gives us the bones of the object, then textures and albedos gives you a skin and personality of that particular object. They transforms a lifeless model into something that feels more aesthetic or authentic. So here's the thought as we move into the AR, VR, any model on that or the technology and the metaverse even, the realism depends heavily on these techniques. So the next time you see a 3D scan of a monument or your favorite video game's character, remember it's not just a shape. It's about how the skin of that model is recovered. So it is more on technology wise. Next we can talk about the depth estimations and epipolar geometry. I'll just give an introduction about that. Let me start with a simple question. How do we as a humans know how far away things are. First thing is that you don't measure with a ruler every time, right? Just see it and just have a calculations of the estimations. You just see it basically. And that's because you have a two eyes. Each eye gives a slightly different view of the world, and our brains uses those differences to estimate the depth, right? So the depth estimation in a computer vision, in a view of a computer, works the same way. But for us, the eyes is given. Instead of eyes, we use a cameras for the input devices. But to make this work, we need to understand the geometry between those two images. We need the knowledge of that also to the computer. And that's where the epibola geometry comes in. So I'll just start with the basics. So depth estimation is simply the process of figuring out how far an object is from the camera, right? From the perception maybe. If you only have one photos, this is hard. There is no direct depth informations, but with the two photos like stereo cameras, suddenly we can triangulate it. So imagine holding one finger in front of your face and closing one eye at a time. Notice how your finger seems to shift against the background. That little shift called the disparity is a key basically. The bigger the shift, the closer the object is. So the smaller the shift, the farther it is. So that's the whole idea behind the stereo depth estimation. We can also talk about the epibola geometry. Now here is where the things get more mathematical but also more elegant. With two cameras looking at the same scene, how do we connect points between them? That is epibola geometric. It describes the relationship between the two images. The rule of these relationships are baked into something called the fundamental matrix. So what is this fundamental matrix is that it is a 3x3 matrix that connects the points in the left images to the lines in the right images. Here is how you to think about it. Suppose you see a person's faces in the left image, left side profile. In the right image, you don't have to search somewhere or everywhere the same faces. So you need only a search along a line called the epipolar line. The fundamental matrix tells you exactly where that line is. First thing is that this reduces the matching problem from the search everywhere in 2D to just search along this 1D line. And that's a huge speed up for the depth estimations. Example, I can say like a two camera are filming a scene. Imagine it. You pick a point in the left image. Using the fundamental matrix, you can calculate the line in the right image where the matching point must lie. That is the magic. So that is how the fundamental matrix works on. Using any matrices, but here the 3x3 matrices will be worked out. Next we have to talk about the essential matrix. The essential matrix is closely related but assumes we know the cameras well. That is, they are like calibrated. With calibrations, we don't just know the lines of the correspondence, we can also figure out the movement between these two cameras. So this means we can recover the rotations and translation between them, right? So in robotics, this is gold because a robot with a stereo camera can figure it out. Did I move forward? Did I rotate left? Or all from the analyze essential matrix. So this is something or next step for technology to improvement. I can say with an example, like think of a self-driving car. It has a stereo camera, right? Using the essential matrix, it not only estimates how far away the other cars are, but also whether its own cameras have shifted due to bumps or the turn or the acceleration or what to react to the next to the obstacles. So this is how it's all work. About the epipolar lines, let's go back to the epipolar lines basically. So here for every point in the first image, its match must lie somewhere on a line in the second images. This means instead of a 2D search areas, you only need 1D search. Think of it like this, like if I tell you I lost my pen somewhere in the field, you have to search the whole area, right? But if you tell it's along the path or the specific location, suddenly your search become too like lot faster and to the specific boundary. That is a power of epipolar geometry, like a direction to that. Example, a person shows up in left images, their corresponding location in the right images must lie along a specific line. That is how the epipolar lines works on. We can talk about the stereo reflections now. The last one trick is that makes lives easier is the stereo reflection, right? So normally the epipolar lines can be tilted or slanted, which makes the searching messy. So what do? We rectify these images, like wrap them so that all the epipolar lines become the horizontal and parallel. Now instead of scanning and slanted line, you just scan along the horizontal row. This makes the depth estimations algorithm much faster and more robust is a strong way. So example, before estimating the depth from a pair of stereo images of a street, we rectify them as visual. So after rectifying it, finding the corresponding points is just matching the pixel across the same row. This is how the stereo reflections works on. I'll just wrap up the things so that you can just able to recap the things. So let's summarize. Like first one is a depth estimation. It's like figuring out the distance from the disparity between the two images basically. Then about the epipolar geometric, it governs the relationship between the two views or the perception. The fundamental matrix connects a point in one images to the epipolar lines in another. The next guidance. The essential matrix here does the same, but also gives a camera motion when come to the calibrator. The epipolar line simply corresponds from a 2D to 1D. That's all the works of that. The stereo reflections makes this even easier by aligning the lines horizontally. But together, these ideas power everything from a self-driving car to a 3D or a 3D moving cameras to AR apps. Next time you play with the VR headset or any games or use a depth cameras, remember it's all math and geometrical quickly or quietly working behind the background. Next, we can talk about the sparse versus the dense correspondence. I'll just give an intro about that. Let's start with a simple idea. Suppose you have two photos of the same scenes. As we discussed before, say a building taken from a slightly different angles. To relate them, the computer has to figure out which point in image matches which point in image B between two point A and B. That's what we call a correspondence. And depending on how detailed we want to be, there are two main approaches. One is a sparse correspondence and dense correspondence. Today we'll break these down, see how they work, and look at the real world examples. The sparse correspondence is like connecting only the landmarks between the two photos. Instead of worrying about every single pixels, we pick a few distinctive points that are easy to recognize no matter the angle, like the corners of the windows, like sharp edges or biopsies of the unique texture. For example, imagine two pictures of the Eiffel Tower, maybe. Even if the photos are taken from a different viewpoint, the corners where the towers meet the ground or the cross beams will still be visible, right, from any angle. The sparse correspondence algorithm says, let's lock or onto those anchor points basically. So one famous method is SIFT. You all heard about that. Scale invariant feature transform. It finds these key points and describes them in a way that makes them robust to change in scales. So the rotations or any lightening also. So even if one photo is zoomed in and the other is taken at a night, SIFT can still match the right points. So example, if you take two photos of a building from a different angle as I told before, the SIFT can match the corners of the windows between them. These match are sparse. So they just handful of points, but they are very reliable onto this. So basically, we can see on to the next topic here. Now let's push further. What if instead of just a few anchor point, we want to match every single pixel from one image to the other? That's a dense correspondence. This much heavier computational because the computer is solving millions of little matching problems. Just imagine. But the result is much richer. You get a dense disparity mapping, right? So think of it like For every pixel in a left camera, you find its partner pixel in a right camera. So then you measure the shift or disparity, but all those disparities together, and you get a detailed map of depth across the whole scene. Example, imagine a two stereo image of a street. A dense correspondence algorithm does not just find the corner of the building. It produces a depth map where you can see how far every pixels, the cars and the road, the street, or it is from camera, right? So this is all which works on. The feature planching is all about, now let's circle back to the sparse correspondence. The process of actually finding the linking these distinctive point is called the feature mapping. We don't just detect the corner or blob, we also describe them using algorithm like SIFT or SURF and ORB. These are the three algorithms used. SIFT is basically used for the fingerprint matching. These descriptors are like fingerprints of the feature to find it matching of that. They allow us to say like the point in the image A is same as the point in the image B, even if lightning or the prescriptions or the perceptives, there can be changes over the images. This is a critical in applications like tracking the object in a video, because example like following the footballs in a matches. It is more difficult when compared to the 2D as well as a video camera on that. The building panoramic photos like stitching the multiple images together, or the structure from motions like reconstructing the 3D shapes from multiple 2D images. Example, when you take a panorama of your phone, the software uses a feature matching to find the overlaps between your shots. It matches the corners of the building or the edges of the cloud across the image and stitches them together seamlessly. So comparing the sparse with the dense, I can say. So you all have one question: which one will be better, sparse or dense? So when answering to this question, it depends on the task. Sparse correspondence is fast and reliable, but it gives you as a skeleton of the key points into that. The perfect for task where you don't need full details like object recognition or image stitching. But when compared to the dense correspondence, it is rich and detailed, but much heavier. Perfect for depth maps like 3D reconstructions or AR VR virtual reality applications where you need a pixel by pixel realism. So it's a bit like the difference between a road map showing only the major cities like sparse versus a detailed GPS map with a single street and alley, the dense or the pictures over that. So this is all about the differences. Let's summarize to this. The correspondence is like matching the points between the images. The sparse correspondence focuses on the distinct landmark like corners or the blobs. The dense correspondence matches every pixels, producing detailed depth maps. A feature matching is the key tool for sparse correspondence powered by algorithms like SIFT, SURF, and ORB. In real system, we often combined the two sparse features to quickly establish the geometry and the dense method to fill in fine details. So here is a thought of for you is that next time you see or use a Google Earth, a Google map and tilt the map into 3D, remember some of that magic comes from the dense correspondence, turning the flat photos into a textured 3D world. Next, we can see with the disparity map. A disparity map is what we get after comparing the two stereo images, like how hard left and right eyes see slightly different views. It shows how much each point in the left image has shifted compared to the right images. So this shift is called a disparity. Since the objects that are closer appear to shift more between the two images, the depth is inversely related to the disparity. First one is a big disparity. The object is closer. The second one is a small disparity. The object is farther. So, example, imagine taking a picture of a car with two cameras side by side. In the disparity map, the car which is close will appear bright because it shifts a lot between the left and the right images. While the faraway buildings will appear darker because they are barely shift. So that's how it works to this. Next we can see about the ransack and alignment. Ransack is a word random sample consensus. Ransack is a clear algorithm, or we can say as a clever algorithm used when you want to find a models like a line, plane, or a matrix. But your data is messy and contains outliners, maybe a wrong or a noisy points. Instead of trusting all the data, ransack maybe in the ransack, they randomly picks a small subset or builds a model from it, checks how many other points fits the model, or repeat the process and choose the models that works best for most of the data. Example, when matching two images, not all detected points are correct matching. Ransack helps to estimate the fundamental matrix by ignoring the bad matches and keeping only the consistent ones. Next, we can talk about the ICP, iterative closest point. The ICP is used when you have two 3D point cloud, like a set of 3 points, and want to align them. It works like this, like for each point in one cloud, find the closest point in the other. Compute the best rotation and transition into the align them. Repeat until the two clouds overlap as well as possible. Example, if you scan a room from a different position, maybe The ICP helps to combine both the scans into one complete 3D model of the room. As we just seen before, the robust estimation is that a method is robust if it can still give good result even when the data has error or outliers. The ransack is a most popular robust estimation technique. Example, if you try to fit a line to a set of points and a few are way off, normal regressions would be skewed. The ransack ignored the bad points and fit the line to the majority. So this is how the robust estimations is worked in ransack. What about the model fitting? This is a general process of finding the best parameters of the model that explains your data basically. So example, fitting a plane to a set of 3D point in a point cloud. With the ransack, the plane will fit the main structure while ignoring the stray points. So this is all about the model fitting in a ransack. Next, we can move on to the one of the last topic is a 3D reconstruction and depth estimation. Think about walking down a busy street with your phone cameras on. As is record, it's not just capturing the flat picture, it's actually trying to understand the 3D world around you. First, it notices a special spot like the corner of a building or a street sign. I call as a sparse correspondence. Then it start matching with almost every pixel between the images. That is a dense correspondence. To figure out what is a closer and what is farther, this creates something like a depth vision, the more detail to that vision or the picture or the model, where a car nearby look closer and brighter and far off building look darker in the disparity mapping we have seen. The drones and the robots do the same thing, but something with a laser or sound waves to scan the world like active range finding. The data they collect can look like a little dots in a space. The point cloud, a blocky cubes like a voxels or a smooth wire shapes like a meshes. But the raw data is messy. That's why smart algorithm steps in. So the ransom helps ignore the bad points and find the real pattern. The ICP takes a scan from the different angles and pieces them to give look like together as a puzzle. So finally, the 3D world is not just made of shapes. It's filled with a color and detail to give more authentic figure to that. That's where the textures and the alidos comes in. They make a virtual car look shiny or a wall look rough. So it feels rough, real or anything. We can texture it. We can feel the picture. So from placing a virtual chair in your living room with AR to helping self-driving cars seize the roads to doctors scanning the organs in a 3D. These techniques lets our machines turn flat pictures into full 3D understanding of the world, much like how our own eyes and brains work together. I would like to conclude this unit with 3D reconstructions and death estimations are all about the teaching machines to see the world in a 3 dimension, just like we do with our own eyes. From directing key features to building the depth maps, aligning the scans and adding texture to that, every steps work together to turn the flat images into a rich 3D models. These ideas are not just theory, they power everyday tools like AR apps, self driving cars, drones, and even in the medical imaging. So we can see to this. I'll also upload the next video regarding the recap of this unit. So you can just go through that. Thank you.